Hello, everybody. Welcome back to class. Is this true? Our last Thursday of the semester. You know the drill by now. We've been doing this for a few weeks. Can you please say hi in the chat if you're here? Suba's here. Taylor says, good morning with the sun. Taylor, here in Winston-Salem, it's going to rain all day. I don't know where you are right now, but hopefully it's sunny wherever you are. Suba, I've noticed that you've started to like to make the simultaneous sip part of your morning routine. Oh, it's raining here. Well, okay. Well, it appears sunny on camera, at least, right here. So we'll get started in, I don't know, half a minute or so. Gives me a reason to wake up. But I've had 2 cups of coffee already. Oh, jeez. Well, just one more sip. Good morning, Emma. Right on time. Well, it's 9 o'clock. So that means it's time for the simultaneous sip. The best part of everybody's morning. So if you have your... Oh my gosh, Emma's also had 2 cups of coffee. Jeez. Good morning, Shutong. So if you have your coffee or your water or your tea and would like to join in on the simultaneous sip, that'd be the time to do so. Good stuff. All right, so I said at the end of class yesterday that we'd start today with some proofs. So let's do that. I guess before we get started, I sent out that survey last night about the final exam. Please fill it out if you haven't yet, because I want to make the decision about the final exam as soon as possible. Ideally, I'd make it today. Okay? So if you haven't filled out the survey yet, it takes 2 seconds, I think. Good morning, Navik. I was nervous you weren't going to be here today. All right, so let's get started. So yeah, fill out that survey if you haven't yet. All right, so let's state and then prove an important theorem in linear algebra. Which is the Cauchy-Shwarz Theorem. It's easy to state, and it's really not that hard to prove. It says, for all vectors u and v in V, some vector space, some inner product space, the absolute value of their inner product is less than or equal to the products of their magnitudes. Okay, so this gives us an upper bound for how big the inner product could possibly be. I'm at the Open University, and my physics exam has been made into an online exam. Navik, I would focus on your physics before you come to this class. And chat wasn't working, but I still had a sip. Great. Okay, so let's prove this. Right? This tells us what is the importance of this theorem. It gives us an upper bound for how big an inner product could possibly be compared to the lengths of the vectors. These vectors don't have to be column vectors. They could be what we've been looking at were polynomials, and what we'll see later. We'll come up with an inner product for continuous functions. But this gives us an upper bound. All right, so let's prove this. So the first case we'll look at is if u is the 0 vector, then the left-hand side is 0, the right-hand side is also 0. So there's nothing special here. So, of course, 0 is less than or equal to 0. So the theorem holds in the case where u is the 0 vector. So let's consider the case where u is not the 0 vector. And we'll let w be the span of u. All right, so w is the subspace. That's just the line through the origin in the direction of u. I guess before we get to the kind of the main idea of the proof, recall that the magnitude of cu is equal to the absolute value of c times the magnitude of u for all c. All right, this fact is going to be important. Okay, so we haven't really done anything yet. We said our first case was if u equals 0, the left-hand side would be 0, the right-hand side would be 0, and we're done. Now we're considering the case when u is not equal to 0. We could take our, well, we're trying to show this. That's equivalent to say, so we aim to show that so if we could show this, that the absolute value of u times v over the length of u is less than or equal to v, the length of v, right? This is the same thing as this. So our goal is going to be to show this. Can I see just thumbs up or thumbs down if we're following the logic so far? Basically, what we're going to do is show that this is always true. And that will imply that this is always true, which is the theorem. Okay, so we'll start with this left-hand side, and we're going to manipulate it. We'll start with this left-hand side, and we're going to manipulate it until we could get something that looks like v. Okay, so starting with the left-hand side, because we don't know this is true, we want to show it's true. So this is equal to, well, we can multiply the numerator and denominator by the magnitude or the length of u. Okay, so why do we do that? Well, we could rewrite this again. Instead of having the magnitude of u squared, that's the same thing as the inner product of u with itself. The inner product is always non-negative, so putting the absolute value around it doesn't change its value at all. But we're doing it like this for what will be the next step. Okay, so this reads u times v over u times u, and then times the magnitude of u. Now we could use this fact here, that this is the same thing as the magnitude of uv over uu times u. What is this? What vector is this? U times v over u times u in the direction of u. Right? This expression should look, at least it should look familiar. And if you're unsure, that's okay. Well, I'll answer for you. This is the projection of v onto the subspace spanned by u, which we call w. So this is the projection onto w of the vector v. Okay, so really what our question asks, we don't want to show that this is less than or equal to v. It's easier if we restate the question, say, show that. So we want to show the projection onto w of v is less than or equal to the projection of v. The magnitude of v. So we want to show that the magnitude of the projection is less than or equal to v itself. So let's just kind of sketch a picture of why we think this might not be that hard to show. So if here is w, that's v. This is the projection onto w. Of v, right? It's an orthogonal projection, so If you project it down, it meets at a right angle. So we want to show that the length of this side is less than or equal to the length of this side. Have you learned any theorems in your high school or middle school math career that talks about the side lengths of a right triangle? Right? Because here we have a right triangle, and we want to discuss facts about the side length. Yeah, so let's use the Pythagorean theorem. Right? It's amazing. You probably didn't think that you'd be using the Pythagorean theorem in a linear algebra class, but here we are. The Pythagorean theorem says the magnitude of the projection onto W of V squared plus the length of this vector So the Pythagorean theorem says this, right? The projection onto W of V squared plus the length of this dotted line vector squared is equal to the magnitude of V squared. Well, since this quantity, V minus the projection on the W of V, the length of it squared, is greater than or equal to 0, we have that the projection onto W of V squared is less than or equal to the length of V squared. And since these lengths are non-negative, we could take the square root of both sides and we get and we showed that showing this is true is the same thing as showing that this is true, which is the same thing as the statement of the theorem. And when you finish a proof, you put a box. Maybe you could put a smiley face in the box if you're really happy with the proof, or you could just fill it in to tell the reader that the proof is done. So any thoughts or questions about the proof here? Again, what this theorem tells us is there's an upper bound for how large the inner product could be, and it's bounded by the product of their lengths. How did we get rid of the V minus? Okay, yeah. So going from here to here, we have equality, right? Pythagorean theorem has an equality. This number here, the one that we got rid of, is at the smallest it could be is 0, but it's often a positive number, right? So if we get rid of this 0 or positive number, it just shrinks the left-hand side, and what's left over is this. So we would do nothing to the right-hand side, and we'd make the left-hand side smaller, basically, is what happens. And so now we have an inequality. right? So think of it just in simple terms. If we had like 4 plus 1 equals 5, and we got rid of the 1, it'd say 4 is less than or equal to 5. That's kind of the logic we're using here. Are there any other questions? Okay. Well, let's use this. Let's use this theorem. So I'm going to. Oh well, we have it written down here. Well, this 4. It's not important. Let's prove another theorem. This one's called the Triangle Inequality. And it says for all u and v in V, some vector space with an inner product. So for all u and v in an inner product space, the length of the sum of two vectors is less than or equal to the sum of their lengths. And the way we're going to show this is we'll show that the length of this sum squared is less than or equal to the sum of the lengths squared. It just makes it a little bit easier to work with. All right, that's the game plan. All right, so let's start with this left-hand side, and we're going to use this Cauchy-Shwarz identity to get to the right-hand side. So let's start with the left-hand side. What's the length of u plus v squared? How can we rewrite this? Does anybody remember how to write, if you have the length of a vector squared, what's another way to write that? Yes, Taylor, exactly. So the length of something squared is the same thing as taking the inner product with itself. Which now we can distribute this. right? If we distribute this out, we get u, the inner product of u and u, plus 2 u times v plus v times v. I said we're probably going to use the Cauchy-Shwarz identity, which involves the absolute value of u plus v. So I claim that this line here is less than or equal to, well, we'll keep the first term the same. And we'll replace this with the absolute value of the inner product of u and v. Right? If the inner product was positive, then nothing changes here. It'd be equality. If this inner product was negative, then the value of the sum will just get larger. Okay, so that's where this inequality comes from. And now we're set up to use the Cauchy-Shwarz identity, right? Because this is less than or equal to So I just wrote CS here, so we know that we use the Cauchy-Shwarz identity to get from here to here. And so maybe we're not sure where to go from here. What is the inner product of u with itself? What is u times u? And then similarly, what is v times v? Well, u times itself is the magnitude of u squared. And v times itself is also the magnitude of v squared. And this magnitude of u squared plus 2uv plus the magnitude of v squared, this can be factored. Into the magnitude of u plus the magnitude of v squared. Which is what we wanted to show, right? Magnitude of u plus v squared is equal to this, less than or equal to this, less than or equal to this, which is equal to this. So magnitude of u plus v squared is less than or equal to this sum, which is what we wanted to show. And this triangle inequality appears in all different branches of math. So if you go on to take like an analysis course or something, for example, you'll be using this triangle inequality all the time. So are there any questions or thoughts about this proof? It's good to get to do a proof every once in a while. All right, well, if there's no questions, we can move on. So we're going to go back to looking at specific inner products. So probably the most widely used inner product inner product space for applications is the vector space which is denoted C of AB, which is continuous functions on the interval AB. Okay, so this vector space consists of all continuous functions on this interval, A to B. And we're going to describe its inner product. Okay, so basically what we're going to do is we're going to consider the inner product we used for polynomials, but make it better. So the inner product we used for Pn involves n plus 1 points. Well, for polynomials of degree at most n, that's enough to uniquely determine the whole polynomial. So that's plenty for a polynomial. But we're looking at all continuous functions, right? So just knowing the values at n plus 1 points does not tell us a lot about the continuous function. It only tells us n plus 1 bits of information. So what we're going to do is we're going to take our interval a to b into n plus 1 subintervals. Of length delta t. Okay, let me see in the comments if anybody has an idea of where this is going. We're taking our interval, a to b, and we're going to break it up into a bunch of subintervals. And what we'll do is we'll take sample points in each of these subintervals. Okay, so what this is going to look like, let's say this is A to B. We're going to break it up. Taylor sees it. She anticipates an integral. I would say that is a wise insight we have here. Yeah, this looks a lot like what you did in Calc 1, I'm sure. Or maybe Calc 2. So our sample points. So here there's n plus 1 subintervals. Maybe this is like T0, T1, so forth. Each of them of length delta t. So we'll take this inner product for Pn, but we're going to scale it by a factor of 1 over n plus 1. Which is equal to, if we solve for 1 over n plus 1 here, that's the same thing as delta t over b minus a. Okay, so that's what we're going to be doing here. So the inner product on Pn was PQ is equal to the sum from I equals 0 to n. I said we're going to factor it. I mean, we're going to scale it by a factor of 1 over n. Right, this was the inner product on Pn, and we said that 1 over n plus 1 is delta t over b minus a. So what we'll do now is we'll now let n get arbitrarily large. Okay, so we'll take the limit as n goes to infinity. This limit, does anybody know what this limit is? How do we express this limit as an integral? This is equal to 1 over b minus a the integral from a to b of p of t times q of t. dt. So this, and typically we drop the factor of 1 minus b over a. So let's define this to be the inner product. Or I guess we should prove that it's an inner product. Okay, so we want to show that this is an inner product for the space of continuous functions. How do we show something is an inner product? Okay, so what are the important takeaways? Maybe you forget all of your calculus, okay, and all of this was just gibberish to you, how we ended up setting up a Riemann sum and all that stuff. We got to this point, and I claim this integral, so you have to remember a little calculus, might be an inner product. How do we show this? Yeah, the 4 axioms. Okay, so we'll probably won't be able to do all 4 of them, but we'll be able to start at least. Okay, so the first axiom is we want to show that this commutes. We could commute and it won't change the value. So we start with f times g. Which is the integral from a to b of f of t times g of t dt. And this is just a product here. So you could switch the order and it's not going to be a problem. And this is exactly g times f. Okay, second, we want to show that f plus g times h is equal to f times h plus g times h. So this is equal to this integral by definition. F plus g of t is the same thing as f of t plus g of t. And now we can distribute this h in.
And then we could break up this integral because the integral of a sum is the sum of the integrals. Right, and this is exactly the inner product of f and h, and this is exactly the inner product of g and h. So condition 2 holds. All right, condition 3. Cf times g is equal to the integral from a to b of Cf of t g of t dt. Cf of t is the same thing as c times f of t. And we can factor a scalar out of an integral. That's another integral rule. Just taught my calc class that last week. And this is just c times the inner product. And then condition 4, f times itself is that. And we know that since f of t squared is always greater than or equal to 0, the integral of f of t squared is also greater than or equal to 0. And the only way that this integral equals 0 with continuous functions, so it's a fact of calculus. So maybe this is kind of a little shady, but you'll prove it if you take an analysis class, but you're probably told this in calculus, or maybe you're being told this by me for the first time. It is a calculus fact that the integral of a to b of f of t squared dt equals 0 if and only if f of t is the 0 function for continuous functions. So we showed all 4 axioms hold, so we have an inner product. I know we went a little bit fast towards the end, but all of this stuff is being recorded, so you could play it back in slow motion if you would prefer. But that seems like a good place to stop. So tomorrow we'll actually compute some of these inner products. So please fill out that survey if you haven't yet. Try to do it as soon as possible because I would like to finalize the final exam tonight. Smash the like button, of course. That's so important. And then tomorrow you have your quiz. It'll be the same setup. So the 8 o'clock students will take it at 8:30, and then the 9 o'clock students will take it at 9:40. I'll stay around for a few minutes to answer any questions, but If not, I have office hours this afternoon, or I'll just see you tomorrow in class. No problem, Taylor. Thanks for answering questions. My exam will be 24 hours. You got this. You got this. 24 hours. That's plenty of time to take an exam. All right. Well, if there's no last minute questions, I'm out of here. Bye-bye.